On the next 6 slides of this screencast, we will examine the greenhouse effect. Our planet is warm for 2 reasons. One is incoming solar radiation from the sun, and the other is greenhouse gases in our atmosphere. We'll look at greenhouse gases on the next slide, but do remember that both of these contribute to the greenhouse effect. First, let's look at solar radiation. When the sun sends its radiation toward Earth, there are 2 types of radiation that reach us: ultraviolet and visible light. About 1/3 of solar radiation is reflected back into space by things like clouds and ice. The UV portion, is mainly absorbed by the ozone layer. So remember, the layers of the Earth was the troposphere, which is where most of weather occurs, and that is 0 to 10 miles above the Earth. And then from 10 to 30 miles above the Earth, we have the stratosphere, and the very lowest portion of the stratosphere, right at about 10 miles above Earth, is the ozone layer. So it's protective. Now, the rest of this radiation is absorbed by clouds and the Earth's surface. And then, once clouds and the Earth's surface, including soil and water, absorb this radiation, they re-emit it as a different type of radiation called infrared radiation. So that's not nearly as complicated as it might look like, but since we don't really talk much about climate change in lab in this remote or online situation, let's take a little bit of a look at that. So you can see that energy comes in waves, and the waves may be more frequent, which is higher energy, or of lower frequency, which is less energetic. So things on the left of this particular diagram, things like gamma rays and X-rays and ultraviolet radiation, are higher energy. That's why ultraviolet radiation can damage the DNA in our cells and cause sunburn. In this tiny sliver of the electromagnetic spectrum, we have visible light. And we observe it as things in the 400 nanometer to about the 800, not quite 800, 750 nanometer wavelength. So an intermediate type wavelength. And we observe colors associated with each of the wavelengths, and I won't go into how at this point in time. Then you can see as you move to lower energy, lower frequency radiation, there's a type of radiation called infrared radiation. And I like to think of it as the heat that almost shimmers off of a hot parking lot tarmac. You can almost see it like waver in the atmosphere, if you will. And that means that the tarmac, this very dark colored, pigmented material that makes up the paving, absorbs higher energy radiation, including visible light, and then it re-emits it as a different wavelength of light called infrared. But there really isn't anything much special about it other than we don't perceive it as a color. It isn't particularly, it doesn't harm us to have infrared radiation. But it does have an effect on the atmosphere, which we'll talk about in a minute. And then going further down here to the right with lower energy, you have things like radar, television, and radio. Okay, so next we'll look at greenhouse gases, and then we'll put it all together in a more diagrammatic portion view. Okay, this is actually screen 2 of 6. So the planet is also warm, not only because of solar radiation, because of greenhouse gases as well. And these are particular gases in the atmosphere that hold some of the heat, hold some of that solar radiation, and radiate it back to the surface. And only a few molecules do that. That's not a common thing at all. So let's look at it in terms of a diagram or figure. So here we have incoming solar radiation that's UV and visible light. Some of it is absorbed by clouds or the Earth's surface, and about 1/3 of it is reflected back from the atmosphere, into the atmosphere, from clouds and the planet's surface, particularly things like snow and ice. Moving down here to 3, the remaining solar radiation is absorbed by other clouds and the surface of the planet, both land, air, and water. And those things become warmer, and then they may emit infrared radiation, a different form of radiation. So much of the emitted infrared radiation from Earth is absorbed by greenhouse gases in the atmosphere, and the remainder goes back off into space. And as the greenhouse gases absorb infrared radiation, they warm and emit infrared radiation, with much of it going back to Earth. The greater the concentration of greenhouse gases, the more infrared radiation is absorbed and emitted back to Earth. And I think that's probably the key statement. There's always been natural greenhouse effect. Without it, our planet would not be warm. It would become an ice cube based on its distance from the sun. And yet it's not. It's warm because we have these small quantities of greenhouse gases. However, when the concentration of greenhouse gases increases, the more infrared radiation is absorbed, and then the more infrared radiation is emitted back toward Earth, and we get warmer and warmer and warmer in that positive feedback loop. So, what gases are greenhouse gases? Well, one of the most abundant is water vapor, H2O, and you know that. There are humid days, days with fog, days with rain or snow. So water vapor contributes a significant amount of greenhouseability to the atmosphere, and it always has, and without it, we wouldn't have a warm planet. However, these others also have existed for millennia, but again, it's the quantity that we need to worry about. Carbon dioxide, or CO2, as you've been introduced to already, is a greenhouse gas, as is methane, CH4. Both carbon dioxide and methane are added to the atmosphere through the burning of fossil fuels, or the extracting of fossil fuels. And so we are raising the levels of these two molecules in the atmosphere, these two greenhouse gases. Nitrous oxide, which in this case is 2 nitrogen atoms and 1 oxygen atom, is also a greenhouse gas, and again, it is produced as a result of air pollutants, typically from either farm fields or certain combustions. Last, we have ozone, which is O3, unlike oxygen, which is O2 that we breathe in. And ozone is grand when it is in the bottom of the stratosphere, but it's not so grand when it's in the troposphere. And last but not least are the CFCs, the chlorofluorocarbons that we have talked about that are now banned, but stay in the atmosphere for many, many decades. So these 1, 2, 3, 4, 5 are in green because they can and do naturally exist in the atmosphere. This last one in purple is only a result of synthetic production by humans. Now, a very important point here. Most of the atmosphere does not consist of these greenhouse gases. They exist in very small quantities, very small. 99% of the atmosphere contains nitrogen, which is a molecule N2, and oxygen that we breathe, which is the molecule O2. So that's 99% of the atmosphere, and they are not greenhouse gases. So 1% of the atmosphere contributes a significant impact, if you will, positive, or when it's not, when it's natural, but when it's anthropogenic, it's potentially a very negative impact. But again, very small quantities do a very large amount of effect. Okay, so this table talks about the major greenhouse gases and compares them. And one of the things that is a takeaway from this table is that it's not only the concentration, which we'll look at in a minute, but it's also how much infrared radiation is absorbed, or excuse me, how much radiation is absorbed and infrared radiation is released by each of those greenhouse gases. And then the other factor, which is how long do they last in the atmosphere. So you can see water vapor, that's very hard to measure. It's very variable. It has global warming potential because there's so much of it. It doesn't stay in the atmosphere very long. Of course, there's a very wide variety there with each weather system, for example, that comes through. But compared with CO2, we can say for sure that its global warming potential is less than that of CO2. If we look at CO2, of the remaining items on this table, it has the highest concentration. Here, this was from, let's see, what year? Well, it was from 2010, and there were 390 parts per million of CO2. Every year that I've given this lecture, the amount or the concentration of carbon dioxide has gone up each year and has to be revised in the slides each year. So this is November 2020, and the current concentration of CO2 is 415 parts per million, and it's continued to rise quite exponentially from the initial measurements. But we'll look at that in a few minutes. Moving on here to methane, or CH4. It's present in much smaller quantities than CO2, but the problem is it is a much stronger greenhouse gas than CO2, and it's estimated to be 25 times stronger in terms of warming the atmosphere than CO2 is. So even though we have smaller quantities, we do have to consider the effect. It also stays in the atmosphere for a relatively long number of years, 12 years. Nitrous oxide, again, very small quantities in the atmosphere, but very great warming potential, and it stays in the atmosphere for many, many years, over a century. And then the CFCs, very small quantities in the atmosphere, but look at that global warming potential. It's quite significant. And as we've already talked about when we talked about the ozone layer, CFCs tend to remain in the atmosphere, not only catalyzing the breakdown of ozone, but here acting as a global having global warming effects on the troposphere, and having that for many, many years to come. So we'll move on from the natural greenhouse effect to comparing natural and anthropogenic sources on the next screencast.